Probably every 10 years, or maybe faster than that, astronomy is turned upside down by a new discovery.
We're missing a huge chunk of the cosmic movie. We know about 5 minutes of the first part of the movie and about 10 minutes of the last, and it's as if we fell asleep during the rest. And so we've got to try, we can guess what happened between the first 5 minutes and the last 10 based on the context of the opening. That's a big chunk of movie to be missing. So we'd really like to be able to fill that in by making measurements, not just guesses about what happened out in space.
We receive light in many different frequencies. It can be optical light, and then we can look at it through your regular optical telescope. But the light also comes in the radio frequencies, not much different than what, like you get your radio signal on your regular radio.
The whole notion of trying to look at radio waves in space came about after accidentally discovering them in 1932. So the amount of energy we're collecting from deep space is minuscule, and so we have to amplify our signal millions and millions of times in order to get that signal above the thermal noise level of all the electronics that it takes in order to amplify and detect these signals. And so radio astronomy really is the search for that needle, the signal, in the haystack of the noise that surrounds us.
Did you know that radio astronomers invented Wi-Fi? No, you didn't know that. That was a byproduct of thinking about how to observe the sky. You could debate whether Wi-Fi is actually useful, but it's very widely used technology that almost shapes our lives these days.
Yeah, without radio astronomy, you'd still be plugged into a cable somewhere.
The exciting results that end up coming out of that project are often not what you set out to do, just because there's so much unknown out there in the universe, and when you put out a new piece of instrumentation or a telescope that can view the universe in a new way, you find things that you weren't expecting. Yeah, so here's C.H.I.M.E. It's 4 100-meter long cylinders that are 20 meters across, and it reflects the signal of the sky as it comes down to the focus below our feet here, to 256 receivers that run along the focal line on each cylinder. Here we have 512 signals coming down from the feed line, and they run along trays under the telescope. Each cable is 50 meters long. In total, there's about 100 kilometers of coaxial cable.
The reason why we can make actually this telescope now is that all of these components became extremely cheap. I mean, the idea of this kind of like massive telescope with lots of receivers is not new. But before, maybe 10, 20, 30 years ago, I mean, this would cost billions of dollars. I mean, advancement in cell phone technologies and fast graphic processing units and computers really aided in getting these components being very cheap.
C.H.I.M.E, the Canadian Hydrogen Intensity Mapping Experiment, was designed to do a one-off experiment, which is do a map of the sky in hydrogen intensity in order to measure the expansion history of the universe due to dark energy. And for that experiment, they need to sit on the sky for 5 years and really understand their instrument extremely well.
Most of the matter in the universe is in form of hydrogen. So by mapping and looking at this transition, we can actually map, like how the matter is distributed in the universe. And that's exactly what we're, poised to do with this telescope.
Particularly what we're looking at with radio telescopes like this one and C.H.I.M.E. is we're seeing this emission that comes from the combination of magnetic fields and what we call cosmic rays. These are really, really high energy particles like electrons and protons. They're actually moving around at relativistic speeds, an appreciable fraction of the speed of light.
The dish that you can see out the window has one beam. C.H.I.M.E. has 1,000 beams. So C.H.I.M.E. is looking at a lot of the sky simultaneously. The dish you're looking at out the window is mechanically driven to point to different parts of the sky. C.H.I.M.E. has no moving parts. It points electronically, but it can only point along the north-south meridian, the north-south line overhead. And we rely on the rotation of the Earth to sweep the sky past. So C.H.I.M.E. will look at the entire sky every 24 hours.
I am probably the only telescope operator in the world that operates a telescope that doesn't have any moving parts. So this instrument, along with looking at mapping expansions of the universe over the cosmic age, is very good to look at the transient objects because we are looking at the sky at all times. So one of the projects that's within C.H.I.M.E. collaboration is search for fast radio bursts.
Yeah, fast radio bursts were originally discovered in 2007 from data that was taken in 2001. They were searching with the Parkes telescope down in Australia for radio pulsars, and they saw this really bright burst that looked like it was coming from way outside of our galaxy, and that's an example of where they discovered something they weren't looking for. It's a mysterious event that we're not sure where it comes from. We know it comes from the most extreme environments in the universe.
We are tackling one of the most important questions of fundamental science.
Since Edwin Hubble in the 1920s, we've known the universe is expanding. And we always thought that eventually that expansion would slow down, that gravity would fight back, pulling the galaxies back together. But about 20 years ago, astronomers discovered that instead of slowing down, the expansion is actually speeding up. We're not clever enough to understand it, but we're clever enough to think up a funny name for it. We call it dark energy. And C.H.I.M.E. is trying to find out what it is. The signal that from the distant universe that C.H.I.M.E. is hunting for is buried under that Milky Way signal by a factor of 100,000. And that's where the technical challenge is.
So we have all this bright emission from the galaxy, which is great for two things. First, it's great because it really helps us understand our galaxy that we live in, particularly gas between the stars, which ultimately is connected to how stars form and to magnetic fields, and to understanding where we come from. But we also have to understand this foreground emission very well because we have to remove it in order to do the cosmology science.
One of the biggest challenges in radio astronomy is interference from intentional transmissions for communications purpose or unintentional garbage that leaks out of cell phones or your video camera here.
This area of spectrum gets more and more populated with cell phone bands, and all sorts of radio interference. So maybe this is the last chance for us really to actually do these observations from Earth.
The good news for any aspiring astrophysicists out there is that there's job security here. There have been times throughout the last couple hundred years where people have made the bold predictions that in a few years there won't be anything left to know, that we're pretty close to wrapping everything up. And of course, every few decades there's some new mysterious thing that we have to try to solve.
So the more we understand, the more questions we'll inevitably have because we'll know what we're missing. So we'll know a lot more in my lifetime. We'll know a lot more tomorrow than we do today. But I don't think we're ever completely understand the universe. It's way too complicated for that.
The coolest things that will come from the future of radio astronomy will be completely serendipitous, and they won't be the things that the telescopes were designed to look at. Who knows in 10 years after C.H.I.M.E's been operating for a while, whether or not there'll be some other magnificent mystery that pops up that telescope could help answer.
I don't think that this quest to understand the universe will ever end.